Hello, sorry I'm not in again. I'm just really not feeling very well, but I made you this video so you can play this in the lesson and you can then just make your notes and things as we're going along. So the first starter question here is which one's the odd one out? So you can have a quick press pause, have a quick discussion amongst yourselves, see what you think. Okay, so it's a little bit of a trick question. I mean, the conversation coming from last lesson is about how the structure of a solid is a regular structure, and yet SpongeBob SquarePants, Morph, and Mr. Jelly all have probably an more irregular than Iron Man anyway, structure to their solid, but they are still a solid because liquids fill the shape of the container that they're in. So once Mr. Jelly has solidified, he will keep his own shape, as does Morph and as does SpongeBob SquarePants. So solids aren't just things like that have a really very regular structure to them in terms of like a macro structure, like a big structure, because just because sponges have holes in doesn't mean they're not solid. Okay, so we're looking at specific heat capacity today. Okay, so this is me on my holiday. It was actually my honeymoon. I am in the Maldives. It's really nice. This sand is really white, okay, and it is really hot. I think this was our little hut thing here. When you came out the hut to get to the beach, it was hot, okay, and actually not very nice because the sand looks lovely, but it's actually made of parrotfish poo. Now, parrotfish eat the coral and then they do really hard poos, and that's what the sand's made of. So when you fall over on it, I actually cut my leg falling over on it. But anyway, why do you think the sand feels so hot and the water is so cold? Just have a quick discussion about it and then let me know. Okay, so what you probably got is that it takes a long time for the water to heat up, whereas sand heats up quickly. So water has what's called a higher specific heat capacity than sand. It takes more energy to heat, probably about 4 times more energy to heat water than it does sand by 1 degree. So if we have a kilogram of each, okay, it takes more energy to heat a kilogram of water by 1 degree than it does to heat sand. So the sand heats up quickly. It also loses that energy quicker. So at night, the sand cools down much quicker, but the water feels warm. Okay, so these are some specific heat capacities of some different materials. So you can see here that the metals have a lot lower specific heat capacity than the liquids, so oil and water, with lead being the lowest, so lead would heat up the quickest here. This is the definition of specific heat capacity, okay? The specific heat capacity, C, little c, annoying because it's the same symbol as the speed of light or the speed of sound in a vacuum. But the specific heat capacity C of a substance is the energy needed to raise the temperature of unit mass, so that's 1 kilogram, of the substance by 1 Kelvin, okay? So instead of degrees C, it's Kelvin, without a change of state. So this is only occurring during the heating process, not when it's melting or turning into a gas. Now, the equation is delta Q equals mc delta theta. Now, we use Q for energy instead of E to distinguish it from work done. So this Q is thermal energy. Okay, it's always called Q. And the delta means change. So change in thermal energy is equal to the mass of the substance you have times its specific heat capacity times the change in temperature. Delta theta is the change in temperature. Now, because it's change in temperature, it doesn't matter if it's in degrees Celsius or Kelvin, but if you want to practice using Kelvin, then this is a good opportunity. So you could do a quick calculation here of the energy that's needed to be supplied to raise the temperature of 5 kilograms of water from 20 degrees Celsius to 100 degrees Celsius. if you pause me, then you can have a go at it, and I will quickly do it too, because I don't think I've put the answer on, and then I'll tell you the answer. Okay, so the answer you should get is 1.7 megajoules, okay? So it's actually 1.68 times 10 to the 6 joules, okay? So 1.7 megajoules. Wow, it's quite a lot of energy, yeah? About the same amount as in a Mars bar. Okay, so there are some different ways that you can measure heat capacity of these things, and I'm going to go through their methods now. Again, I've never seen these come up in exam questions, these methods. That doesn't mean they're not going to. After each one of these, you should pause the video and then make the notes. So listen to me go through it, then pause the video and then make your notes. So, first one is to determine the specific heat capacity of solids such as lead. So basically you have a tube, and in that tube you put some of your metal, but they're in pellets, so like these little balls, and in the end here you put a thermometer. Now if you turn the tube upside down, gravitational potential energy is converted into internal energy when the shot hits the bottom. So GPE turns to kinetic energy. When it hits the bottom, it will turn into internal energy and raise the temperature. Now, the tube is inverted each time, so you do it more than once. So when the shot hits the bottom of the tube, you tip it back up the other way. So the temperature of the shot is recorded after n inversions. So that could be 10, 20, 100 times of turning it upside down. So we're going to look at M is the mass of the lead shot. L is the length of the tube. So the loss in gravitational potential energy after n inversions will be, so gravitational potential energy is E equals mgh. So we've got mg and then our h, the change in height, is L. And then we need to multiply that by how many times we changed it. So let's say after 1, the amount of gravitational potential energy was 10 joules. If you did it 10 times, then you would have increased the energy by 100 joules. Okay. Now that gravitational potential energy is turning into internal energy, and the internal energy is Q equals mc delta theta here. So we can put these two terms equal to each other, as I've done here. And what you can see is the m's cancel each other out, okay? And then if we want a term for specific heat capacity, we then rearrange the equation for C. There are energy losses, so there's friction with the side of the tube. So as the balls travel down, they will rub against the side of the tube and they will heat the tube up instead of the balls. So that gives them some energy losses. We also lose some energy as sound as well. What I want you to do is write this down. I want you to make sure that you can rearrange this equation properly to get C. So don't just copy it down. Get to this point, then rearrange for C yourself and check you can get to the right. If you can't get it right, you need to ask someone for help. So press pause when everyone's ready to move on. We'll move on. Okay, so this is the way to find the specific heat capacity of a proper metal, so like a lump of metal, something like aluminium. You might have done this at GCSE. We will do it at some point. I've not booked it for next week, but maybe the week after you can have a go at it. What you have is your lump of metal with a heater inside and a thermometer, okay? The heater is turned on and that will heat up the lump of metal, and the thermometer will measure the change in temperature. This is the circuit diagram for it. You measure the current and the voltage and the time that it's left on for. So you have a metal block of mass M and you put a 12-volt heater inserted into the hole, and that measures the amount of energy. Now the thermometer is inserted into the second drill hole and measures the change in temperature. It doesn't work very well if you just measure it, because it's measuring the air here. So often you can put some Vaseline or some water in there so that it measures the metal, heats the fluid, and then the thermometer measures the temperature of the fluid, because it's better. It covers the ball then at the bottom. Now, the energy transfer is electrical energy from the heater turning into heat in the metal block. So the electrical energy we supply to the heater is IVT. So that equation is given to you in your data sheet, okay? IV is power, so power times time. So the current times the potential difference times the time it's left on for. Now that is being directly converted into internal energy of the block, so MC delta theta here. So we can put them equal to each other and then rearrange the equation for C. Again, pause the video, write down what you need. You don't really need this circuit diagram. If you want to draw this quickly so you know what it looks like, that's fine. Make sure you can rearrange the equation for C. Okay, and then we have the specific heat capacity of a liquid. Now, you probably use these in chemistry. They're called calorimeters. What they are essentially is a cup with a lid on it. They're probably a bit more fancy than that, but they're a cup with a lid on it. So what you have here is an insulated cup. You have a fluid inside with a lid, because obviously we want to stop heat loss by convection. And then there's a thermometer, and there's actually a stirrer in them because we need the heat to be evenly distributed, and if you set up a convection current in here, the hot water will be at the top and the cold water will be at the bottom. Now this one's a bit more complicated because any heat you supply with your heater, which is here, is going to heat the water and the cup. Okay, it's going to heat both. So let's look at the mass here. You have a liquid of a known mass, okay, and it's put in the insulated calorimeter. And the calorimeter also has its own mass and specific heat capacity. Now, a 12-volt electrical heater is used to supply a known amount of energy, and a thermometer is inserted to measure the temperature rise. So you supply IVT, so the current times potential difference times time, same as last time, amount of energy. And that is being used to heat the liquid and the calorimeter. So the internal energy of the liquid increases by its mass of the liquid times the specific heat capacity of the liquid times the change in temperature of the liquid. Okay. Now the energy needed to heat the calorimeter, okay, will be the mass of the calorimeter times the specific heat capacity of the calorimeter times the change in temperature of, and these two temperatures will be the same because they'll be in thermal equilibrium. So they'll be at the same temperature. So we've got our electrical energy supplied being shared between the liquid and the calorimeter. Okay, and if you want to find the specific heat capacity of the liquid, the rearrangement of this looks horrible, so it's much easier to leave it like this. Okay, you would fill in the values here, and then you can find the specific heat capacity of the liquid. Okay, so pause the video, make your notes, and then press play again. We've got one more to go. Okay, the last one is the continuous flow heating. So this is something that might happen like in an electric shower. So if we look at this electric shower, what happens is the water will pass through copper coils, which are heated by an electrical heater. So inside here somewhere, there'll be some electrical coils which are heating up water, okay, and their electrical energy is being supplied to do that. Now, for the mass of liquid passing through the heater in time t, so let's say we time how much water flows through the heater in 10 seconds, okay? Okay, we are going to assume it's flowing at a steady rate. So every second we're going to assume the same amount of water is flowing. So we're not going to turn the power up or down. And we're also going to assume no heat loss to the surroundings, because this is a magic physics land where we make things easy on ourselves. Now, the electrical energy we supply per second, so the power of the shower, yes, will be I times V, and that will be equal to the mass per second, so mass over time, okay, that flow, so the flow rate times specific heat capacity times change in temperature. You can see if we just move the T over here, we get IVT equals MC delta theta, which is the same as the equations we're looking at. So this just gives us an equation for power, and because showers have the water's flowing rather than stationary, it allows us to have a flow rate, so the mass flowing per second. So that small rearrangement just helps us see the situation a little bit clearer. Now, initially the shower's cold, so the flow rate, the water flowing through is not in thermal equilibrium with the coils of wire. But eventually it will stabilize, and when the outflow has reached a steady temperature, the water of the coils doesn't change. The temperature of the coils, sorry, does not change. So you only need to measure the energy supplied to the coils. So basically it's saying, well, the electrical energy you supply to the coils is then turned into the internal energy of the water, okay? So you don't need to measure the temperature of water, you can measure the temperature of the coils because that will be the same. So this is a nice equation to use. Actually, this is the equation that comes up most often, and what they mostly tried to get you to work out is the flow rate, so mass divided by time. Same thing, if you have a solar heating panel on your roof that heats up water, the energy gained per second by that water is MC delta theta over T. It's the same thing, it's the power that you get. Okay, there are some questions in your book that you can have a go at if you have some time. Thank you for listening. I hope you have a nice day.